Hi, welcome to the next video. So let's work on example 7.15. Okay, so we're going to let x and y be continuous random variables from exercise 7.8. Okay, so to remind you what happened in exercise 7.8, we had our PDF, so I'm going to write solution here. Okay, so first our PDF, our joint probability density function, f of x comma y, is equal to 2xy plus 3/2 y squared. And this is for 0 less than x less than 1, 0 less than y less than 1, and 0 elsewhere. Okay, so this was from example 7.8. Okay, so from exercise 7.8, that's the joint probability density function. Okay, so what we're going to do now in this example is for part A, it's actually part of the solution is, never mind, that's not part, that's part of the problem. Okay, so that's the joint probability density function, f of x comma y. Part A is find f sub capital X of x and f sub capital Y of y. Okay, so let's do that. F sub capital X of x is equal to the integral from negative infinity to infinity of f of x comma y dy. That's by the definition. Again, the definition of the marginal probability density function for any variable x. Okay, x is continuous. So we're using the definition for continuous random variable x. Okay, and so we're going to integrate, but now this is for x. The only y's where f is non-zero, it's 0 everywhere else, is from 0 to 1. So we're only going to need to integrate between 0 and 1, because every other possible value of y, little f is 0. So the integral from 0 to 1 of f of little f of x comma y, which is 2xy plus 3/2 y squared. And this is dy. And when you calculate that, you get x plus 1/2. And this is for 0 less than x less than 1. And it's 0 everywhere else for every other possible value of x, right? We're thinking for this function, we're inputting x values. So when x is between 0 and 1, you get little f sub capital X of x is x plus 1/2. Or when x is any other value, then that is 0. Okay? So we now found f sub capital X of x, the marginal probability function of continuous random variable capital X. Now we're going to find the marginal probability density function of continuous random variable capital Y. That's f sub capital Y of y. That's the integral from negative infinity to infinity of f of x comma y dx. That's equal to the definite integral. So with respect to x, it's from 0 to 1 of 2xy plus 3/2 y squared dx. Okay, so now we're integrating from 0 to 1 with respect to x, because that's the only x values where f is non-zero. And then you integrate that, and you get that's equal to y plus, remember now it's with respect to x, that was respect, so we're going to get a different value here. This is y plus 3/2 y squared. And this is for 0 less than y less than 1. And then it's going to be 0 elsewhere. Okay? So now that is the marginal probability density function of continuous random variable capital Y. This piecewise function. Okay, and so what I did quickly for you is that this differential is that, and that differential is that. Okay, and so now we found, for part A, we found that and that. Okay, so maybe write down this is equal to this, and that is equal to that. Okay, so we're going to need these two later, and so it's good if you write them down now. So when I refer to them later in the next the other part solutions, you have them written down for you there. Okay, there's not enough room on the board to have all this. Okay. Okay, so I calculated this and got this, and I calculated this and got that. Okay. Let's go to part B. That's little f, right? That's little f, and so you should write that down too. That's little f. Okay, these two you should write down. Write down that that's little f. Also, make sure you have that. Okay. So it's three functions you need to keep track of for the later solutions. Okay, those two, and make sure you have this one also. This is the joint probability density function of x and y, right? Continuous x and y. Okay, so we have those three now. Okay, so on the side, I'm going to just remind you of something. We have this, and we have this. Okay, we have these three functions, and so we can use them if we need to for another problem. Okay, so now for part B, we want to find f sub capital X of x given y and f sub capital Y of y given x. Okay, so let's do that. So f sub capital X of x given y, by definition, that conditional probability is f of x comma y over f sub capital Y of little y. Okay, and so that's equal to, this is for y values strictly between 0 and 1, this function. And that's because the y values only, right, little f is only non-zero for little y between 0 and 1. Okay, so you'll only have to worry about those values of y. So now this is now equal to, well, little f from before, right? Little f from before is 2xy plus 3/2 y squared, divided by that, which we found was y plus 3/2 y squared. And which this is equal to, when we simplify it, is 2x plus 3/2 y divided by 1 plus 3/2 y. And this is for, I'm going to have to, the things we have are this, and that. Okay, we have those three functions. Now this is for 0 less than x less than 1. And now this function is 0 elsewhere. Okay? Okay, so then that's okay, so that's that function. That's f of x comma y, that's f sub y, y. Divide, and you get that. For 0 less than x less than 1, you have f sub capital Y of y given x. That's equal to f of x comma y over f sub capital X of x by definition. And that's equal to 2xy plus 3/2 y squared divided by now f sub capital X of x, which is x plus 1/2. And this is for 0 less than y less than 1. And this is 0 elsewhere. Okay, so f of x comma y is 0, right? If it's not both true that x is between 0 and 1 and y is between 0 and 1, right? So you get the 0 here. Now if x is between 0 and 1 for this, and y is between 0 and 1, then f of x comma y is this divided by that, which is that. Okay, and so we now found both of these functions, and so we are done with part B. Okay, so I'll leave this on the board for a moment also so you can write this down. So you need to write these down and have them for the next board. So we also have f sub capital Y of y given x, and we have f sub capital X of x given y. Okay, we have these 5 functions. We had the first 3 before this board, and we added these 2. We found these 2 now in part B. So write all this down. Okay, so you're going to need this for later. Okay. Okay, so we found these conditional probabilities in part B. Okay, so let's continue. I'm going to leave this top part here. These are the 5 functions we have. Okay. Okay, depending on what the question's asking, in future parts, we need certain ones of those 5. We have, so part C, the same example 7.15. Find the probability that 0 is less or equal to x less or equal to 0.5, and the probability that 0 is less or equal to y less or equal to 0.4. Okay, find those 2 probabilities. The probability that 0 is less or equal to x less or equal to 0.5, so I wrote this in the last video. This is equal to the definite integral from 0 to 0.5 of f sub capital X of x dx. Right? It's a probability of a range of x values, and you can use the marginal probability density function of x, of continuous x, in this way to calculate that. It's the definite from 0 to 0.5 of f sub capital X of x dx. And so what is f sub capital X of x? We found it before. For x between 0 and 1, which is all of the x's between 0 and 0.5, we get that function is x plus 1/2 dx. And so when you compute that differential, you get 0.375. And so that differential is that. Just as, right? So as side work here, how you compute that definite integral. Definite from 0 to 0.5 of x plus 1/2 dx. What is an antiderivative of x plus 1/2? It's 1/2 x squared plus 1/2 x. Okay? And so you take that in, and that you could use any one you want for the fundamental theorem of calculus. I chose that one. So with that antiderivative, you go from 0 to 0.5, and so you get 0.5 is 1/2. So I'm going to write 1/2 here instead of 0.5. And so it's 1/2 of 1/2 squared times 1/2 squared plus 1/2 times 1/2. That minus plugging in 0. 1/2 times 0 squared plus 1/2 times 0, and all that in brackets also. And so it's this antiderivative value from the upper limit minus the antiderivative value, same antiderivative value at the lower limit of the integral. And so this is 1/2 of 1/2 times 1/4 is 1/8, plus 1/2 times 1/2, which is 1/4, 1/8 plus 1/4, minus 0 plus 0, which is 0, minus 0. So 1/8 plus, that's equal to 1/8 plus 1/4. That's 1/8 plus 2/8, that's 3/8. And 3/8 as a decimal is 0.375. And so that F integral is equal to 0.375. 1/8 is 0.125, and so 3/8 is 3 times 0.125, which is 0.375. So that F integral is 0.375. Okay, and so I just showed you how you calculate that F integral and get that. That's what the side work is. Okay, it's justifying that step there. Okay, so I'll call this star, and this is star side. Why that equals that. Okay, so let's keep going. So now let's do the other probability. So now the probability that 0 is less than or equal to y, less than or equal to 0.4. That's equal to the differential from 0 to 0.4 of f sub capital Y of y dy. And so that's equal to the differential from 0 to 0.4. What's f sub capital Y of y? We got it. It was y plus 3/2 y squared dy. All right. So now that's this, and then dy after it. And you calculate that differential, and you get 0.112. Okay, so that differential is 0.112, and so that probability that y is between 0 and 0.4 inclusive is 0.112. All right, and so that's the second probability in part C. And so we found this probability here, and we found this probability there. It's a 0.5 there. Okay, as side work, I'll show you why that differential equals 0.112. So as side work. So the differential from 0 to 0.4 of y plus 3/2 y squared dy. And that's equal to an antiderivative of what's in the integrand. One antiderivative is 1/2 y squared plus 1/2 y cubed. Okay, that's the antiderivative of that, because you take the derivative of 1/2 y squared, and you get y, and take the derivative of 1/2 y cubed, and you get 3/2 y squared. And so, and then you get that. So this is an antiderivative of the integrand there, and you value it from 0 to 0.4. And so then you value it from 0 to 0.4, you get 1/2 times 0.4 squared plus 1/2 times 0.4 cubed, and then minus 0. Minus when you plug in 0, which is 0. So you get this minus 0, which is 0. You get this minus 0, which is this. So this is that. And so you calculate that. And so you get 0.4 squared, which is 0.16, divided by 2 is 0.08, plus 0.4 cubed is 0.064. And half of that is 0.032. And so 1/2 times 0.4 cubed is 0.032. So 0.08 plus 0.032 is 0.112. And that's the answer. Okay. 800s plus 300s is 1100s and an additional 2000s. So 0.08 plus 0.032 is 0.112. Okay, on a test you can use a calculator. You can use a calculator so you don't have to do this in your head. Okay, but I like to do as much as I can in my head because I don't like to rely on a calculator or anything. Okay, so that differential is equal to 0.112. That justifies that step. So I'll call this double star. Call it double star. And so this is double star. Okay, and so that is part C. And I calculate that differential for you also. 0.112. Okay, so let's go to part D. Okay, we still have those 5 functions from before. From parts A through parts A and B. part C we calculate two probabilities, so we didn't add a function to our list of known functions. So part D is find the probability that 0 is less or equal to x less or equal to 0.5 given that y is equal to 0.3. Okay, just that one probability. So the solution here, the probability that 0 is less or equal to x less or equal to 0.5 given that y is equal to 0.3 is equal to the definite interval from 0 to 0.5 of f sub capital X of x given 0.3 dx. Let me just equals to that. Okay. This is the marginal probability. This is the conditional probability that x is equal to x naught. X is equal to this, given that y is equal to 0.3. But now we're looking at a range of x values from 0 to 0.5. And so I'm going to add up the values from x equals 0 to x equals 0.5. So I'm going to integrate this from x equals 0 to x equals 0.5. So it's integrating with respect to x. Okay? And so what is f sub x of x given y? Right? So that function is, so f sub x of x given y naught. We said before, in this problem, we found that this was equal to 2x plus 3/2 y naught over 1 plus 3/2 y naught. Okay? So in this problem, the y naught is the 0.3. And so f sub x of x given y is equal to 0.3 is equal to 2x plus 3/2 times 0.3 divided by 1 plus 3/2 times 0.3. Okay? So 2x plus 3/2 times 0.3, 1 plus 3/2 times 0.3. Okay, and so that is f sub x of x equal to 0.3, so that's right there, right? So we just substitute this for that. All right, and then you calculate that definite integral, and you get that's equal to 0.3276. Okay, so that definite interval is 0.3276, and so that's the probability that x is in this range of values given that y is equal to 0.3. So when you have a conditional probability where the first variable here is a range of values, you want to integrate this function. Okay, so that's D. Okay, so we found that probability. So did that. We're done. Okay. With that, part D. Okay, so let's continue to part E. We're done with part D, and now we're going to do part E. Okay, so part E. So for part E, find the probability that 0 is less than or equal to y, less than or equal to 0.4, given that x is equal to 0.2. The solution? The probability that 0 is less than or equal to y, less than or equal to 0.4, given that x is equal to 0.2, is equal to the integral from 0 to 0.4 of f sub capital Y of y given x, given x is 0.2, given x is 0.2, yeah, just that. Okay, so we're just going to add up the conditional probabilities from y equals 0 to y equals 0.4. So this is dy. So this is the integral from 0 to 0.4 of f sub y given x is 0.2 dy. And so f sub y of y given x naught, we said before, was 2x naught y plus 3/2 y squared divided by x naught plus 1/2. Okay, so we're just going to do that, but now the x naught here is 0.2. So f sub y of y given 0.2 is equal to 2 times 0.2 times y plus 3/2 times y squared divided by 0.2 plus 1/2. Okay, so substituting. The functions are weird, but you're just plugging in. Okay, a lot of the weirdness is just plugging in. Expressions are weird, but it's substitution. Okay, so then you have that. And so this is equal to the definite integral from 0 to 0.4 of this expression here. This is f sub y of y given 0.2. So you just plug that in for this, right? And so you substitute that for that, and you get 2 times 0.2 times y plus 3/2 y squared divided by 0.2 plus 1/2. So that's f sub y of y given 0.2, and then integrate that from 0 to 0.4 with respect to y. And you calculate that definite integral, and you get 0.0914. Okay, so that definite integral is 0.0914. And so the probability in E is equal to 0.0914. And that's the end of that one. All right, so this might look hard to integrate. It's easy because 0.2 plus 1/2, that's 0.2 plus 0.5, that's 0.7. And so you're just dividing this by 0.7. So you're getting a coefficient times y plus 3, another coefficient times y squared. And so you find an antiderivative very easily for that, and then you use fundamental theorem calculus, right? So that's not difficult to compute, and that's equal to 0.0914. Okay, so that's parts A through E of example 7.15. And so this example is not that. Okay, so we found this probability here. Okay, so now I can erase everything, including those 5 functions, because we're not done completely with this example. It's always helpful to write the list of functions we have, because with all these functions flying around, it might be easy to lose track of what you've already figured, what you've already found, what you may not have found already. Okay. Next section is 7.2.6, and that is called the multinomial distribution. Okay, 7.2.6, the multinomial distribution. So definition 7.6. Let n and k be positive integers. Let p1 to pk be numbers such that the sum from I equals 1 to k, a piece of I is equal to 1. And 0 is less or equal to a piece of I less or equal to 1 for I from 1 to k. The multinomial probability function function f is defined by f of x1, comma x2, comma dot dot dot, comma xk is equal to n factorial over x1 factorial x2 factorial dot 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 x sub k factorial times p1 to the x1 times p2 to the x2 times dot 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 times p sub k to the x sub k. For integers, x1, x2 dot 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 to x sub k are equal to 0, such that the sum from I equals 1 to k of x sub I is equal to n. Okay, so this is a definition of the multinomial probability function. Okay, definition 7.6. Let n and k be positive integers. Let p1 to pk be numbers such that their sum is 1. And each one is between, so let p1 to pk be numbers such that their sum is 1, and each one is between 0 and 1 inclusive. The multinomial probability function f is defined in this way. For integers x1 to xk being non-negative or greater than or equal to 0, such that their sum is n. Okay, so here we have another probability function. Okay, it meets all the conditions of a probability function that we defined earlier in the class. Okay, and so, for instance, if you want to find the probability of exactly x sub I occurrences of outcome a sub I for I equals 1 to k, this is equal to the probability x1 is equal to little x1, x2 is equal to little x2, and so forth. X sub k is equal to little x sub k, and that's equal to okay, so this is the probability where each of those x values to each of these corresponding little x values, that probability is equal to n factorial divided by x1 factorial times dot 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 times x sub k factorial, the product of all those factorials, times p1 to the x1 times p2 to the x2 dot 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 p sub k to the x sub k. All right, so that's how you use this probability function to find a probability of something. The probability exactly x sub I occurrences of outcome a sub I from 1 to k. So if you have k outcomes and you want to find the probability that each outcome happens a certain number of times, then the probability that each of those outcomes happen a certain number of those times is n factorial divided by the product of the x's, the factorial of all those x's, times p1 to the x1 times p to the x2 times dot 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 times p sub k to the x sub k. Right, these probabilities have to add up to 1. Each one is between 0 and 1 inclusive. The x's, x1 and xk, the sum of them have to add up to n. N is good, and then n factorial here. Okay. So this is the multinomial probability function f, and it's using it to calculate this probability. Okay, so I'll leave this on the board for a moment so you can write stuff down. Okay, so the next section. Okay, so 7.2.7, the bivariate normal distribution. So the bivariate normal distribution so definition 7.7. Let mu1, mu2, sigma 1, sigma 2, and p be constants with sigma 1 positive, sigma 2 positive, and p strictly between negative 1 and 1, not including negative 1 and 1. The function f of x comma y, which see this is a big function here. F of x comma y is just a lot to write down. F of x comma y is equal to e to the negative 1 over 2 times 1 minus p squared. It's a negative here in front of that. Okay. Times, I'll put a bracket here. Times e raised to the product of these things, negative product of these things, times x minus mu1 over sigma 1, that whole thing squared, minus 2p times x minus mu1 over sigma 1 times y minus sigma 2 minus mu2 over sigma 2 plus y minus sigma 2, y minus mu2 over sigma 2, that fraction squared. End of bracket. E raised to the negative of that product. Then that whole thing, including the e negative, that whole thing in the numerator, and the denominator of this fraction, 2 pi divided by 2 pi sigma 1 sigma 2 times the square root of 1 minus p squared. That's f of x comma y. Okay, I'm going to move the f of x comma y so it's centered here. This is equal to f of x comma y is equal to that fraction. The function f of x comma y equal to that for any real number x and any real number y is the bivariate normal probability density function. Okay, and so that is the bivariate normal probability density function. Okay, so this is another PDF, another probability density function. Okay, so it's definition of the PDF. I'll leave it on the board so you can write it down. It's just another probability density function, just a weird looking one. Okay, so I'll give you another moment to write this down. Okay, let's continue. Okay, so 7.3 is next. 7.3 is independent random variables. So 7.3 independent random variables. So 7.3.1 is the definition of independent random variables. Okay, so let's define independent random variables. Definition 7.8. Let x1 to xn be random variables. Discrete or continuous. Discrete or continuous. With probability functions f sub 1 of x1 to f sub n of xn, respectively. And multivariate probability function f of x1 to xn, the n random variables are independent if f of x1 comma x2 comma dot 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 comma xn is equal to f sub 1 of x1 times f sub 2 of x2 times dot 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 f sub n of xn for all values x1 to xn of capital X1 to capital Xn respectively, except at points, just make it a little bit harder, except at points of discontinuity. Okay, so definition 7.8. Let x1 to xn be random variables, discrete or continuous, either one, with probability functions f sub 1 of x1 to f sub n of xn, respectively, and multivariate probability function f of x1 xn. Period. The n random variables are independent if, so I underline independent because that's what we're defining here. It's a definition of n random variables, of n random variables being independent. So they're independent if f of x1 to xn is equal to f sub 1 of x1 times f sub 2 of x2 times dot 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 times f sub n of xn for all values of x1 to xn of capital X1 to xn respectively, except at points of discontinuity. Okay, so where little f here is discontinuous, you do not need that equation to hold. Okay? All right, okay, so that's the definition of n random variables, continuous or discrete, being independent. Okay, so write down the definition, and then in the next example 7.17, I'll give you an example where we show that two random variables are independent. So you'll see how this definition is applied to show that two are independent. Okay, two random variables are independent. Okay, so I'll give you a moment to write down this definition, definition 7.8. Okay, so let's go. So next is the next example. So example 7.17. So example 7.17, x1 is the value on a die, and x2 is the number of heads from one coin flip. Okay, x1 is the value on the die, x2 is the number of heads from one coin flip. So f sub 1 of x1 is equal to the probability that capital X1 is equal to little x1. Okay, so it's a value on the die, right? So for x1, you have a die, and the numbers are from 1 to 6, and you roll them, and what number is at the top of the die? All right, and so the probability that the value on the die is any particular value from 1 to 6 is 1/6, right? And that's for x1, 1, 2, 3, 4, 5, or 6. Right, for any of those values, the probability that you roll one of those numbers is 1/6. And then f sub 2 of x2, that's the probability that your random variable x2 is equal to little x2 is equal to some value little x2. Well, x2 is the number of heads from one coin flip. And so if you toss one coin, there's two possibilities, right? You either get heads or you get tails. So actually, I'll write it this way. You have one coin flip, and you either have heads or you have tails. And so the probability of one head is 1/2. The probability of 0 heads is also 1/2. So the probability capital X2 is equal to little x2 is 1/2 for x2 equal to 0 or 1. Right? The probability that there's 0 heads is 1/2, and the probability there's 1 heads is 1/2 from one coin flip. Okay, so now we have f sub 1 of x1 and f sub 2 of x2. Now, if you want to know the joint probability density function of x1 and x2, right, what is the probability of an outcome of one roll of the die and a certain coin flip, a certain number of heads? Well, that's just going to be 1/12 for any of the values of x1 from 1 to 6 and x2 being any of its values 0 or 1. Right? And so no matter, you have to choose two values, one for x1 and one for x2. But for any given choice, the probability of that happening is 1/12, right? The probability that you roll a 2 and you get 1 head is 1/12. The probability that you roll a 4 and then you get 0 heads is also 1/12. And so f of x1 comma x2 is 1/12. Okay? So now we have that. So we also see, therefore, from all of that above, we see that f of x1 comma x2 is equal to 1/12, but that's equal to 1/6 times 1/2, and 1/6 was f sub 1 of x1, and that's times 1/2, which is f sub 2 of x2. And this is for all x1 and x2. So what I showed here is that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2. And so by our definition of independent random variables, that means capital X1 and capital X2 are independent random variables. And so therefore, capital X1 and capital X2 are independent by definition. So by the definition of independent random variables, capital X1 and capital X2 are independent because we showed little f of x1 comma x2 is equal to little f sub 1 of x1 times little f sub 2 of x2. By the definition on the last board, definition 7.8, that means that capital X1 and capital X2 are independent. Okay, so I tried to exaggerate with the capital and lowercase, right? So this is capital, this is lowercase, right? This is capital, that's lowercase, capital, lowercase. Right? The lowercase are for when you're denoting particular values of the random variable capital X1 or capital X2. Okay. All right, so in example 7.17, we see how we hopefully you see the definition better of independent random variables. Okay. By this example, we proved that rolling a die and flipping a coin are independent events. Are independent random variables. Rolling a die and getting the number of heads from one coin flip, those are independent random variables. Okay, so I'll leave this on the board for a moment so you can write things down. Okay, let's go. Okay, so 7.3.2. X1 and X2 are independent. Event A is the event that capital X1 is equal to some value little x1, and event B is the event capital X2 is equal to little x2. Okay, so X1, X2 are independent if and only if. That's the notation. That's the biconditional. That's notation for the words if and only if. Probability of A intersection B is equal to the probability of A times the probability of B. Okay, so this is section 7.3.2. And so in this section, I want to point this out, right? That X1, X2 are independent random variables. And if you say event A is the event that X1 is equal to some fixed value little x1, and event B is the event that random variable capital X2 equals some fixed number little x2, that statement is equivalent, has the same truth value as saying that the probability that both those events happen is equal to the probability that event A happens times the probability that event B happens. Okay, so those are equivalent. Okay, so that comes directly from the definition of independent events, right? From the definition of independent events, we get the probability of, we get f of x1 comma x2 is equal to, so I'm going to separate, so at the top there, this is just me explaining. We have that little f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2, and of x2. And so the analogy here is that this is this is that, and this is that. The probability of A is the probability that x1 is equal to little x1, that's this. The probability of B is the probability capital X equals little x2, that's that. The probability of A intersection B is the probability that capital X1 equals little x1 and capital X2 equals little x2, that's that. Right? This is the probability that capital X1 equals little x1. This is the probability that capital X2 equals little x2. This is the probability that capital X1 is equal to little x1 and, or just comma, capital X2 is equal to little x2. Okay. This is the probability this equals this and this equals this. This is the probability that equals that, this is the probability that equals that. And so hopefully you can see how these two statements are equivalent, have the same truth value. One is true, the other is true. One is false, the other is false. Okay, so that's 7.3.2. Okay, let's keep going. Okay, so next is 7.3.3. Independent random variables. Derived from independent experiments. Okay, so independent random variables derived from independent experiments. Okay, so we're going to have independent experiments, and from them we're going to get independent random variables. So let's look at part A here. A says, let's say capital E is an experiment. Let's say capital S is the sample space for that experiment, capital E. And let's say capital X is equal to a random variable on your sample space capital S for that experiment capital E. Capital E, the experiment capital E is repeated n times under identical conditions. The random variables x1 to xn are independent random variables. If x sub I is the random variable on the ith performance of E, under identical conditions. Ith performance of E from 1 less or equal to I less or equal to N. Okay, so this is one case, we call part A, example A, of how you derive independent random variables from independent experiments. Okay, so let's capital E be your experiment, name for your experiment. Capital S is the sample space for E, the set of outcomes, simple outcomes for your experiment E. Capital X, let capital X be a random variable on the sample space capital S. If capital E, we're going to say experiment capital E is repeated little n times under identical conditions. So we're going to do the exact same experiment little n times. The random variables x sub 1 to x sub n are independent random variables if x sub I is the random variable on the ith performance of E. So if you're performing your experiment E, capital E, n times, and you assign the random variables x1 to xn to each time you do the experiment. So the first time you do the experiment, x sub 1 is the random variable for the first time you do the experiment. Capital X sub 2 is the random variable for the second time you do the experiment. X sub 3 is the random variable for the third time you do the experiment, up to including the last time, the little nth time. When you do the experiment the little nth time, x sub little n is the random variable for the nth time. And so x sub 1 to x sub n, those random variables you got from the n repeated times you do the same experiment E, those n random variables are independent of each other. Okay? And so the conclusion is that the random variables x1 to xn are independent random variables. Right? By the definition of independent random variables, that means that the multivariate probability function f of x1 to xn is equal to the product of f sub 1 of x1 times f sub 2 of x2 times dot 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 times f sub n of x sub n. Right? So if you look back at the definition of independent events, knowing that x sub 1 to xn are independent, you can get the equation from that previous definition. You can use that equation for these n random variables. Okay? It tells you the relationship between those n and random variables. Now, if they're independent, there's a relationship you can use, right? That equation. Okay, so that's A. That's one way that you can get independent random variables from independent experiments, by just repeating the same exact experiment under identical conditions n times and assigning a separate random variable for each time you conduct the same experiment. Okay, so that's A. And then, okay, so B, I'm going to erase A and write B so that I don't run out of room. And so B, so for B, let's say E1 to En are separate and distinct experiments. So in A, we're repeating the same experiment n times. And here we have n separate and distinct experiments, E1 to En. The outcome of E sub I is no way dependent so the outcome of experiment E sub I is no way dependent on the outcome for e sub j when I does not equal j. So for instance, the outcome of e sub 1 is in no way dependent on the outcomes from e sub 2 to e sub n. That includes any subscript. So the outcome of e sub 7 is in no way dependent on the outcome of e sub 1 to e sub 6 and e sub 8 to e sub n. Okay? So S1 to Sn are the sample spaces, the set of outcomes are the sample spaces for experiments E1 to En respectively. Right? So that means that S1 is the sample space for E1, S2 is the sample space for E2, and so forth. Sn is the sample space for En. If X1 to Xn are random variables, defined on S1 to Sn respectively, then they are independent random variables. The conclusion is that you get independent random variables. Okay, so part B says if you have E1 to En are separate and distinct experiments. Okay, they're completely different, they're separate and they're distinct. The outcome of each E sub I is no way dependent on the outcome for E sub j when I is not equal j. So the outcome of any one experiment is not dependent on the outcome of any of the other experiments. It's not dependent on the outcomes of any of the other experiments. Okay, S1 to Sn are the sample spaces for E1 to En respectively. So those are the sample spaces for those n experiments respectively. And if X1 to Xn are the random variables defined on S1 to Xn respectively, meaning X1 is the random variable defined on S1, X2 is the random variable defined on S2, and so forth, Xn is the random variable defined on Sn, then X1 to Xn, they are independent random variables. So the conclusion is that then they are independent random variables. So here, if we have n separate and distinct experiments, where the outcome of any one experiment is no way dependent on the outcomes of the n minus one other experiments, then you get n random variables that are independent, x1, xn, when you assign each of those respectively to your n experiments, right? Okay, and so this is a second way that you can get n independent random variables by doing n separate and distinct experiments where the outcome of any one experiment is not dependent on the outcomes of the other n minus one experiments. That makes sense? It's a lot to say. Okay? So here's the second way you get independent random variables. And so the conclusion that we want to draw from this A or B is that if x1 to xn satisfy A or B, the A or B I'm talking about, this B and the last A I just wrote, A or B. So if x1 to xn satisfy A or B, then they are independent by definition 7.8. Okay? So the conclusion is if you have a situation or problem where you have n, x1 to xn random variables and they satisfy A or B, then they are independent. Right? And so by definition 7.8, 7.8 is the one where you have the definition of independence where f of x1 xn is equal to f sub 1 of x1 times f of 2 of x2 times dot 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 f sub n of xn. Okay? So if you have a problem where you have an experiment repeated n times, or that's A, or if you conduct n experiments where they're separate and distinct and none of them, the outcome of any one does not depend on the outcome of any other, if either of those two things happen for your n random variables x1 xn, then they are independent. Okay? And so the idea here is you have a problem, you notice that your n random variables satisfy A or B, you then conclude by this that they're independent, and then you can use from the definition the relationships of you can use that equation, f of x1 xn equals epsilon of x1 times f of epsilon of xn. Then you can use that, find the separate probabilities, multiply them, and you can then get the multivariate probability function from knowing that they're independent. Okay? Okay, and so that is that. Okay? And so I'll leave this on the board for a moment so you can write it down. Okay? Okay, and so then this concludes this lesson, and I'll see you next time.